It's a pleasure to be here tonight. I have a question for the audience. Have you ever played Noughts and Crosses? I expect the answer to that is yes. Have you won at Noughts and Crosses? The answer is still a resounding yes. In fact, is it possible that you win at Noughts and Crosses quite frequently and might therefore be led to believe that you're actually quite good at this game? Well, so I have bad news for you. Turns out that you winning at Noughts and Crosses is less to do with you being good at playing Noughts and Crosses as it is with your opponent not being quite so good at it. So before I go into more details about why that is, I thought I should very briefly explain how Noughts and Crosses works. Okay, so we draw a 3x3 grid on a piece of paper. And there are two players, player 1 and player 2, and they take turns placing crosses and noughts in the cells of this grid. And the aim of each player is to get 3 of their symbols on a line, vertically, horizontally, diagonally. The game ends when one of the players has achieved this, and if all of the cells have been filled without 3 noughts or 3 crosses on a line, the game ends in a draw. So a typical game might look something like this. Actually, I'm going to make all my crosses red in this talk and all my noughts blue. Mathematicians like to think about this problem in terms of colors, but really I could have just used noughts and crosses, but I just think the colors make the slides a bit more appealing. So here we go. I started by placing my cross in the top left-hand corner, and my opponent has placed her nought in the center. My next move is to place a cross in the bottom left-hand corner, and she responds by blocking my potential 3 on a line here, and so on, and we continue. And she blocks me every time, and the game ends in a draw. Okay? It actually turns out that my opponent played rather optimally here. If she'd placed her first nought in the corner here, I could have forced a win. But as it stands, the best thing I can achieve is a draw. And in fact, I have to be quite careful not to lose. So what I'm saying here is actually that there is no winning strategy for the first player. Now, what's a winning strategy? A strategy is simply a set of instructions that you follow. So if my opponent does X, I will do Y. And a winning strategy is a set of instructions that guarantee that you will win this game at the end. So why am I saying that there is no winning strategy for the first player? Couldn't there be a winning strategy for the second player? Well, it turns out, given that the game is completely symmetric, so it's the same for both players, if there was a winning strategy for the second player, I, as the first player, could actually just steal it. So I have an advantage by going first. Okay. I'm not going to explain to you tonight why there is no winning strategy for the first player, or indeed show you how to play optimally at Noughts and Crosses. I'll leave you with a reference, a YouTube video where you can learn about how to do this. Well, the reason is that it's actually, despite its apparent simplicity, a rather complex game. If you think about it, there are many, many possible alternative moves the players can make. And to give you a taste of how complex it really is, so have a look at this chart here. So this actually gives an optimal strategy for the first player. So my move as player 1 is always given by the largest red symbol. So my very first move is given by the big red cross in the top left-hand corner. Then I need to check what did my opponent do. So my opponent placed her nought in the center. So if I look at all of the 8 alternative outcomes, she placed her nought in the center. So I then reduce my attention to this square in the middle. And so my next optimal move is given by the largest red symbol that you see, so the red cross here, and so on. You follow this through, and you see there are quite a lot of outcomes where the first player actually wins, where there are 3 crosses on a line, and player 1 wins. But there are also quite a few, and you can barely see them. They're these really, really tiny squares that end in a draw. And this is the best thing that either player can achieve, guaranteed to achieve in this game, is that it ends in a draw. So, in fact, there are only two possible draws, really, in this game. So they look like this, up to symmetries, rotating it, flipping it over. So it really is a rather boring game. And you might start off playing Noughts and Crosses because you're bored, but I suspect after a short while you'll be just as bored again. Now, fortunately, there is a way of making this game more interesting. For example, we could try in playing it in more than 2 dimensions. So 2 dimensions, that's the plane. And here is an example of such a game. You can kind of see this. It consists of 3 layers of the 3x3 grid. And again, the aim is to get 3 of your tokens, or in this case, they're colored tokens instead of noughts and crosses, 3 on a line. So you have all the lines we had before, so diagonally, vertically and horizontally in each of the layers, but we have a lot more lines, namely ones that go across the layers, such as this yellow, the line here consisting of the yellow tokens, as well as ones that run diagonally across all 3 layers. Okay? Now, it turns out that there is actually a winning strategy for the first player in this version of the game. And if you get bored or lost in the rest of this talk, you might want to think about what that winning strategy is. It's not too difficult. What's more, this game can actually never end in a draw. So we'll come back to why that is. Again, so you could argue actually that makes the game a little bit uninteresting. And so people have looked at other variants of this game. So here is my next one. It's called Cubic. I think it first appeared after the Second World War. It was quite popular in the 60s and 70s. So you may not be able to see this very well, but there are 4 layers now in this game. And each layer consists of a 4x4 grid. So this is just a larger version of the game that we had before. I actually had a picture where you could see this a little bit better, but it didn't have fun for everybody written across it, so I chose this one. Okay, so here the aim is actually to get 4 on a line, so you want to have a complete line made of your symbols or your color. Okay. In this game, a draw is possible, but there is still a winning strategy for the first player. So that was found in 1977 by Oren Potashnik with the assistance of a computer. It's quite complicated, and again, so I'm not going to tell you what it is. But again, the fact that there is a winning strategy probably means that perhaps in the long run, this game is not so interesting. However, I invite you to play it online. There are many online simulations, and there's probably an app for it too. It's really quite challenging. Okay. Now, how do we go about analyzing these games? So what I'd like to do is find some kind of representation of this game that allows me to understand what it means to have 3 in a line. So remember when we looked at tic-tac-toe at the beginning, we just simply drew a 3x3 grid on a piece of paper. So I'm going to replace this now with a 3x3x3 cube in 3 dimensions. So that would be studying the first 3-dimensional variant of tic-tac-toe. Okay, so each position in this game that can be occupied by one of the symbols is given by one of these little subcubes. Well, how many are there? So it's a cube of side length 3. So there are 3 times 3 times 3. That's 3 to the power 3. That's 27 subcubes. And I can assign a coordinate to each subcube so that I can refer to it. Maybe I'll refer to the center of the subcube. So for example, I could look at the cube in the center on the top layer. And that would have coordinates 2, 2, 3. So I step 2 to the right, 2 to the back, and all the way to the top. So that gives me the coordinates 2, 2, 3. Excellent. Let's look at what it means to have 3 crosses on a line. Let's do an example. So I have a line of crosses in the bottom row in the front layer. And I'll just write down what the coordinates of these crosses are. So they're 1, 1, 1, 2, 1, 1, and 3, 1, 1. Simply the x-coordinate increases by 1 at each step. And if I wanted to be a little more abstract about it, I could have written this as star 1, 1, where my wildcard star runs from 1 to 2 to 3. Okay? I simply, to get the 3 crosses on the line, the coordinates of these 3 crosses, I simply replace the wildcard by 1, then by 2, then by 3. Okay, just to get this, to understand this a little better, let's look at another example. Oh, and I make a definition. This is a combinatorial line. Let's look at another example to understand this better. So here I have crosses in the subcube labeled by 1, 1, 1, 2, 1, 2, and 3, 1, 3. And again, I could have written this as star 1 star, where the star is replaced by first by 1, then by 2, and then by 3. This, while a perfectly acceptable line in the sense that we commonly use the word line, is not one of these combinatorial lines. So when I write down the coordinates, I have 1, 1, 3, 2, 1, 2, 3, 1, 1. And you see that the second coordinate stays constant, so that's good. The first one increases from 1 to 2 to 3, which is also good. But the third one goes from 3 to 2 to 1, which kind of runs in the other direction from the first one. So strictly speaking, this is not quite a combinatorial line. For the purposes of this talk, I could have swept this under the carpet. Because there are more ordinary lines than combinatorial line. Every combinatorial line is also an ordinary line. So if I can guarantee a combinatorial line for one of the players, then he or she will also have an ordinary line. The question is, can we actually guarantee a combinatorial line of crosses or noughts for one of the players? But before I answer that question, I want to just illustrate briefly why this kind of more abstract representation of the game is actually useful to study further variance. So one modification we can make very easily to this cube is we can actually increase its side length. So for example, we could study the 4 by 4 by 4 game, cubic. And all that means is that the coordinates now run from 1 to 2 to 3 to 4, rather than just between 1 and 3. Right? So for example, the 4 by 4 by 4 cube contains a subcube with the coordinates 4, 1, 2. So 4, 1, 2. Yeah, that's it. Okay. This representation also allows us to play this game in more than 3 dimensions. For example, we could try and play noughts and crosses in 4 dimensions. Now, easy, Tiger, I hear you say. Actually, I don't hear anything. I can't visualize 4 dimensions. Well, neither can I, and I don't actually know anyone who can. But in terms of this representation, it's very easy to understand what the 4th dimension would be. So why is this a 3-dimensional picture? Because I can describe the position of every subcube here by 3 coordinates. Right? I have an x-coordinate, a y-coordinate, a z-coordinate. The 4th dimension simply means that every point in my space has a 4th coordinate. So I'm not going to try and draw this because I can't, but imagine there's a 4th coordinate, like the w coordinate, and we just give it a value. So a 3 by 3 by 3 by 3, a 4-dimensional cube of side length 3, might contain a subcube with coordinates 3, 2, 2, 1. Okay? And what's great about this is that I can use this definition I made of a line, a combinatorial line, earlier, in exactly the same way as I made it for the 3-dimensional cube. I just say a combinatorial line is something that consists of a point that has some fixed and some variable coordinates, and the variable coordinate goes from 1 to 2 to 3. Right? And that gives me 3 on a line in a 4-dimensional cube. Okay. Now that we have a workable representation of this, we can start asking some questions. For example, I told you earlier that the 3 by 3 by 3 game, in the 3 by 3 by 3 game, the first player has a winning strategy, and I assume you're still working on that one. I also told you that the 4 by 4 by 4 game has a winning strategy for the first player. I also told you that that was very complicated. What about a board of side length 5? Well, it turns out that even for a board of side length 5, there are very few things that we really do know. For example, Is it true that in 5 by 5 by 5 noughts and crosses, either player can force a draw, such as in 3 by 3 tic-tac-toe? Is it true that 5 by 5 by 5 by 5 noughts and crosses, so 4-dimensional noughts and crosses with side length 5, has a winning strategy for the first player? And we don't know what the answer is. Now you say, why don't you just give this problem to a computer? Well, you saw how complex even the 2-dimensional noughts and crosses game was. There are simply too many possible plays here for a computer to analyze. So we have to do something a little cleverer than just churn through data. In fact, very often in mathematics, it pays to ask a stronger question. And the stronger question I'm going to ask is the following. So no matter how we arrange the noughts and crosses in a cube of side length 5, can we always guarantee a full combinatorial line of noughts and crosses? So 5 noughts or 5 crosses in a row, horizontally, vertically, diagonally. Now, why is this a stronger question? Because notice that I've completely removed the game from this question. I'm just saying I want you to consider a cube of side length 5 with some noughts and crosses in it, and no matter how they're distributed, can you guarantee that there is always a full line of noughts or a full line of crosses? Okay? In particular, I'm not requiring that half the symbols in the cube are crosses and half of them are noughts, right? I could say, is it true if I just have 2 crosses and everything else is noughts? So this will have implications for the actual game. So if you can guarantee a full combinatorial line in any distribution of noughts and crosses, then you will certainly be able to find it in a distribution of noughts and crosses that is the outcome of a game. The good thing is that the answer to this question is yes. But you see there are 3 little dots here that should make you worry because there's going to be a but in the next line. So it's only true if the dimension that we're playing in is large enough. Okay, so what I've just stated for you is a special case of a mathematical result that's called the Hales-Jewett theorem. So it was proved in 1963 by Alfred Hales and Robert Jewett. And in fact, they proved this not just for cubes of side length 5, but for any side length that you can imagine. You could play on a board of side length 127. They would be able to tell you that if you play in high enough dimension, then there will always be a full combinatorial line. In fact, their theorem doesn't just apply to noughts and crosses. In fact, you can take any number of symbols or any number of colors to fill your cube with. And this is only a very special case. So what's the implication for the game? The implication for the game is that no matter how big the board is that you're playing on and how many players you play with, if the dimension is large enough, then noughts and crosses can never end in a draw. And that means if you get to go first, then you win. Now, there are 2 issues with this. Of course, I say you win, but I haven't actually told you how you win. And in fact, we don't know how you win. So I told you that we know what the winning strategy is for boards of side length 3 and for boards of side length 4. But for 5, we have no idea. The second thing that should worry you when you read the statement of this result is that it says, if the dimension is large enough, what on earth does large enough mean? And again, we basically don't know what it means. So looking at a board of side length 5, I know that there is a dimension, a minimum dimension that guarantees that there is a winning strategy for the first player, but I don't know what that dimension is. It could be 4, which is the question we had on the previous slide. It could be true for dimension 4, could be true for 7, could be true for 121. In fact, I can't even prove to you, beyond any doubt, that it's less than 1 billion. And to give you an even better idea of quite how poorly we understand this problem, I'll tell you a little bit about how fast things grow on the next slide. Okay, how large is large enough? There are going to be a few numbers on this slide. You can close your eyes and wake up again on the next one. But it's not too bad. OK, I'm going to look at some integers, 1, 2, 3, 4, 5. Right? We all know what these are. And really, in the back of your mind, you should think that this is the length of the board that we're looking at. Right? And I'm going to perform a very simple operation on these integers. So the first thing I'm going to do is I'm going to double these integers. So if k equals 1, I'm going to look at 2 times k, and that's going to give me 2. 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and so on. I can fill this table very easily. OK, that sequence doesn't seem to be growing terribly fast, but we all know that there are things that grow very fast. We usually say that they grow exponentially fast. So what does that mean? Something like this. So I raise 2 to the power k. So 2 to the power 1 is just 2. 2 to the 2 is 4. 2 to the 3 is 8, and so on. And you can see that this sequence grows a little bit faster than the first one. In fact, what I could have done to get the second row from the first one is I could just have, to get the second row, I could just have applied the function in the first row to each entry in the cell. So for example, the function in the first row was the doubling function, right? It times everything by 2. So I times this entry by 2, I get 4. I times this one by 2, I get 8. I get times this one by 2, I get 16, and so on. You get the idea, right? And this is simply because this function here is basically k times the function we had in the first row. Takes the function, applies the same thing k times. Applying multiplication by 2 k times gives you 2 to the k. We can carry on with this idea. So if we were to apply the process of exponentiation k times, we would get the following kind of function. So we call it the tower function. So instead of taking 2 to the k, I take 2 to the 2 to the 2 to the 2 k times. Okay? You can see why it's called a tower function. So what are its values? Again, it starts at 1, very conveniently. 2 to the 2 is just 4, so perfect. 2 to the 2 to the 2, that's 2 to the 4, that's 16. Okay, so it already grows a little bit faster. Now, what is 2 to the 2 to the 2 to the 2? That is 2 to the 16, because I'm just applying the function from the row above to this cell. That is a very large number, which we'll get to in a moment. If you like, the way I could write this, and you can really close your eyes here, is I could say that the value of t at k is just the exponential function applied to the value of t at k minus 1. And what that gives you, for example, for t3 is exactly that, as we already discovered. So when I apply this to t of 4, it means I'm applying the exponential function to this value here, to 16. So it's 2 to the 16. That is 65,536. That is a fairly large number. Now, what do I have to do for the next cell? I have to take 2 to the power 65,536. That is a very, very, very large number. In fact, it has over 20,000 digits. And so on. You can see that we're going to stop calculating here. OK, why stop here? So there's a fourth row in this table. It has the appropriate name, wow function. OK, so I define it in exactly the same way as I've defined all of the other functions in this table. So basically, I apply the operation in the row before, just k times. OK, it starts with a 2. They all start with a 2. So what am I doing here? I'm applying the tower function to 2. So that's 2 to the 2. That's still 4, so that's not looking too bad. Now, what is it I'm looking for next? I am looking for two to the 16. So, sorry, a tower of 2s of height 4, which is precisely this number here, 65,536. Now, what do I have to do next? I have to take a tower of 2s of height, what's given in this cell here. Okay? So that is a tower of 2s of height 65,536. That is an unbelievably large number. And you can see how this just gets worse. Okay, so you have some idea of what I mean when I say some numbers get very large. Okay, so here's the bad news about our fantastic result, that if you play Noughts and Crosses in large enough dimension, then there is a guaranteed first player win. Well, it turns out that if you ask me what's the minimum dimension I need to play in for a board of side length k, well, the best thing I can tell you, it's in dimension at most w of k, where w of k was the function we had on the previous slide. So in particular, when the side length of my board is equal to 5, I'm saying you need to play in dimension at most w of 5, where w of 5 was a number that I couldn't even write down. So this doesn't sound terribly useful, and indeed it's quite bad, and it gets worse. So if you ask me what is the minimum dimension you need to play in with 3 friends on a grid of side length 7, so that you can be guaranteed to win if you go first, I will throw up my hands and admit that I have no idea. Okay. Of course, this question is slightly preposterous for 2 reasons. One is that, I mean, who plays in more than 3 dimensions, really? Let's be honest. Well, actually, I'm about to show you a game that very naturally sits in 4 dimensions. You wouldn't notice, but it does. So you can all play in 4 dimensions. Your next objection might be that you actually need 3 friends to play with who are crazy enough to go for this. Well, the second thing I want to convince you of in the second half of the talk is that you can actually play this game by yourself. And we'll talk about that in a moment, too. Okay, so now let me show you this fantastic game that lives in 4 dimensions. So it's called Set. It looks like this. I will open it. It consists of a deck of cards. There are 81 cards. And I'll tell you a little bit about what you can see on each of these cards, but I'll do this on the slides because you wouldn't be able to see it anyway. Okay, so it consists of 81 cards. Each of the cards displays some symbols, shapes. There are 3 different shapes. There are diamonds, ovals, and some squiggly things. They come in 3 different colors, green, red, and purple. They come with 3 different shadings. So there are the solid ones, the empty ones, and there are some striped ones. And on each card, you have a 1, 2, or 3 of these symbols. Right? Okay. And you can see that there are 81 cards in total because 3 times 3 times 3 times 3 is 81. Okay. Why is this game called Set? So a combination of 3 cards is called a set. If for each of these 4 attributes, so color, shape, shading, and the number of symbols that are displayed, either all 3 cards are the same or they are all different. Okay, I can't really process that, so I'll show you an example. So here are 3 cards with 1, 2, and 3 squiggly lines. They're supposed to be purple. I think they are on my laptop. They're all solid. And yes, so I claim this is a set because they all have the same color, they use the same shading, they're all the same shape, but the number of symbols displayed differs on each card. So it's 1, 2, or 3 of these squiggly things. Let me show you another example. This one is slightly trickier. So I have 2 red squiggles, 1 green diamond, and 3 purple ovals. So again, that's a set because we have 3 different symbols, 3 different numbers of symbols, and we have 3 different colors, and they're all solid because I can't do empty or striped. Okay. Now that I've showed you what a set is, let me show you what's not a set. So this is an example of a set of 3 cards that's not a set. A collection of 3 cards that's not a set. So we have 3 green ovals, 2 red diamonds, and 3 purple squiggly things. That's not a set because there are 2 cards displaying 3 symbols. Okay? So I could have defined a set to be any combination of 3 cards unless it can be described by the phrase 2 of one type and 1 of the other. And just so we're absolutely sure we're all on the same page, can you find a set amongst these 6 cards? Top left. Yes, okay, I think we have it. So we have the empty green diamond, the striped purple squiggly things, and 3 solid red ovals. Okay, now I think we've understood what a set is, but this is pretty much how the game goes. So there's a dealer, and he or she deals out, I think lays out down up to 12 cards initially on the table, and the first person to spot a set cries set. And if you get that correct, you get to keep the cards, and the person with the most cards at the end wins. Good. So again, we need to find a way of thinking about this game in a slightly more abstract in a slightly more abstract way. And it turns out that it's actually closely related to the kind of problem we were studying before. Turns out I can identify each of the 81 cards with a point in a 4-dimensional cube of side length 3. Of course, I already told you I can't do 4 dimensions, so ignore this 4th axis for a little moment. So I have a 3 by 3 by 3 cube. I have the x-axis, which indicates a number of symbols on the card. I have the y-axis, which indicates a shape. So the front layer in my cube is all ovals. The middle layer may be squiggly things, and the rear layer may be the diamonds. And my bottom layer consists of everything that's purple. My middle layer consists of everything that's green, and my top layer consists of everything that's red. And then the 4th coordinate kind of tells me what the shading of each of the symbols is, but as I said, I can't draw it. What's nice about this representation, right, so A, it sort of shows you that this is actually a game that naturally sits in 4 dimensions, but you can easily imagine adding further dimensions to this game, right? So for example, I could add a background color to each of the cards, or I could add a fancy border, like a solid one and a dotted one and a striped one. So there are all kinds of things I could do to increase the number of dimensions. The game would just get very hard to play. As it is, it's already not easy. Okay, so what is a set in my cube? A set, well, let's look at an example, with something like this combination of cards, 1, 2, and 3 purple ovals. Let's look at what this is in the cube. Oh, look at this. It's 3 on a line. That's good news. But maybe we should test the hypothesis that sets are always 3 on a line. So let's look at another one. That's 2 green ovals, 1 red oval, and 3 purple ones. Okay, still 3 on a line. Very good. Okay, so we're convincing ourselves that actually sets kind of correspond to lines in this cube. I'm going to destroy this illusion, only temporarily though. Okay, look at this one. 1 green oval, 2 red ones, and 3 purple ones. Here we are. That doesn't look very much like a line, but I'm going to try and convince you that it is a line anyway, which is where my high-tech prop comes in. Okay, so I've drawn this configuration of crosses on a piece of paper. You can all see this, right? Okay, now this is where the magic happens, if it happens. Here you go. So can you see 3 on a line? Very good. So we're going to call a line of this type a modular line. So for those of you who know about modular arithmetic, this is basically because we're working modulo 3. So, and because I wasn't quite sure whether this demonstration was really going to work, I actually put an alternative way of viewing this on the slides, which is I could just place a second cube exactly identical to my first one right next to the other one. And I could draw in these symbols, and you can see that there are 3 on a line right across here. Okay? So they're not exactly on a line, but they're sort of on a line in adjacent cubes. Excellent. So we've understood what a set is, and what the basic objects in this game are. So I think we're well equipped now to actually ask a question, and the question that we're going to ask and answer is, how many cards do you need to lay down on the table before you are guaranteed that there actually is a set, right? So the dealer starts by laying out 12 cards, but it turns out many times there isn't a set amongst these 12 cards. So, you know, how many more cards do you need to put down on the table? According to this representation that we just established, this is exactly the same as asking how many crosses do I need to place in the 3 by 3 by 3 by 3, so the 4-dimensional cube of side length 3, before I am guaranteed to get one of these modular lines. Okay. And I'll just pause with that second question for a moment. So this actually explains what it means to play noughts and crosses by yourself. So when you're playing noughts and crosses by yourself, obviously placing 3 on a line is not terribly interesting. I mean, you just do it, and you're done. But actually, it turns out that trying to avoid getting 3 on a line is quite challenging. So you can start placing some crosses, and you will place more and more until, you know, you basically can't escape creating your modular line. And the answer to this question basically tells you what your personal record could be, at best, playing noughts and crosses by yourself, just playing crosses, basically. Okay, now, turns out that the answer to this particular question, so the 4-dimensional cube of side length 3 is 20, and we've known this since the 1970s. But what mathematicians have been very interested in for actually several decades is to ask this question not just in the 4-dimensional cube, but in a cube of any dimension. So if you like, an n-dimensional cube where n can take any value. So it could be the 1,532-dimensional cube, for example. Okay, so this is actually a famous and difficult and long-standing problem. So how many crosses can you place in the 3 by 3 by 3 by 3 cubes of dimension n without creating a modular line? People have been working on this. There's one thing you can say relatively easily. So I claim that you can place at least 2 to the n crosses without creating a modular line. So how do I do that? And I can actually explicitly tell you that. I just place a cross in every subcube whose coordinates are only 1 or 2. So why does that avoid any kind of line? Because in order to get a line, in at least one direction, I have to take a step, and I have to take another step to get the third cross. And so that means that in at least one direction, my coordinate must have changed from 1 to 2 to 3, right? Unless I stay constant everywhere. And that means that if I pick only points whose coordinates are 1 and 2, if there are no coordinates that are 3, there are 2 to the n of them, then I can avoid creating a modular line. Okay. Well, it turns out that very, very recently, a group of mathematicians have made enormous progress on this problem. So here they are. That's Ernie Krut of Georgia Tech in the US, Seva Lev of the University of Haifa in Israel, and Peter Powell from Budapest. So they tackled and essentially solved this problem for the 4 by 4 by 4 by 4 cube, n times. Okay. Actually, when I was preparing these slides, I noticed you could kind of claim that they form a set. So they work on 3 different continents. You know, they wear 3 different outfits. They have 3 different backgrounds, and they're all male. Okay. I'm not going to state for you what they actually proved, but what I will say is that their work, which literally dates from about 6 weeks ago, 7, has been enormously influential in a very short time span. And how can this possibly happen that something, well, we just heard about contagions, that a result has so much impact? Well, if they had proved what they proved 250 years ago, someone would have had to write a letter to their colleagues, and someone would have had to get on a horse and transport that letter to wherever it was, and someone probably would have had to get on a ship. And so on. So this is a letter from Goldbach to Euler in 1742, in which he actually posed a very important conjecture. And these days, we have a website that's called The Archive. Actually, you can't see this very well. It's ARXIV. And people can upload their latest work to this website, and everyone can read it the next morning. It's free, accessible to anyone. I just press the PDF button, and here it is. It's almost instantaneous. So here you can see this is the work of Kroot, Lev, and Pach, and it was uploaded on the 5th of May, 2016. So the next day, we all had a very exciting day at work. And in particular, this work was picked up very quickly by two other mathematicians. So that's Jordan Ellenberg of the University of Wisconsin and Dion Giswit from the Netherlands, Delft, I believe. And they were able to adapt this work to get the result for this long-standing problem in the 3x3x3x3 cube. And then they posted their own article. So this is from the 30th of May. That's slightly inaccurate because they actually did it before then. But you see that the time span of communicating this was actually very, very short. OK, so let me tell you what they proved. So they proved that you can place at most 2.756 to the n crosses in your 3x3x3 cube without creating a modular line. Okay, just to remind you, we've already seen that we can place 2 to the n crosses, and they're saying you can place at most 2.756 to the n. So the truth lies somewhere between these two numbers. Now the good news is, and this is a reason why this has made such a splash, is that these two functions at least look vaguely similar. I mean, it's 2 something to the power n. In fact, you can do a tiny bit better than 2 to the n. So, you know, this is really quite a breakthrough. Having said that, of course, if you look at individual values of n, so let's say look at n equals 13, so 2 to the 13 is 8,192, while 2.756 to the 13 is about 500,000. So I guess you could argue that we still don't really understand this problem. Now, what's even more amazing about their result is that the proof is actually extremely elegant and simple. It's so elegant and simple that I can give you a very, very small idea of how it works. But I really like this quote of Frédéric Chopin that I found. Simplicity is the final achievement. After one has played a vast quantity of notes and more notes, it is simplicity that emerges as the crowning reward of art. And I think if you replace the words notes by symbols and art by mathematics, this is a very accurate description of the situation here. So, what do they do? What's the main idea behind this result? So there are going to be a couple of equations on the next slide, but again, you can just ignore them. It's mainly pictures that I want you to look at. So I have a very simple function here, a linear function y equals x minus 1. So that's the graph of this function. It intersects the x-axis at x equals 1. So we call this a 0 of this function, because when I said x equal to 1, then y is equal to 0. And you can see that for a linear function, this happens at most once. So if your line happens to be parallel to the x-axis, it's never going to intersect. It's not going to have any zeros. But if you have a slope, a non-zero slope, then you can have at most one intersection. Let's look at something slightly more complicated, like a quadratic polynomial, y equals x squared. You can ignore the rest here. OK, so clearly this doesn't have any intersections with the x-axis. There are no zeros here. But I can move it a tiny bit and see that there are 2 zeros. And it's also not too difficult to convince yourself that no matter how you shift it, left, right, center, how you might sort of stretch it, there are not going to be any more than 2 zeros for a function of this type of parabola. And I can go on. I could look at a cubic polynomial, so a polynomial of degree 3, something like this. And again, it's not so hard to see that it has at most 3 zeros. So there's a very elementary fact in mathematics that a polynomial of degree d has at most d roots, meaning places where it is 0. Okay, how does this help you prove something about crosses in a high-dimensional cube? So here is how the argument goes. So suppose you have a set that consists of, not a set in the sense of the game, but a collection of crosses that you've placed in a cube with no 3 on a line. And suppose you can find a polynomial which is 0 everywhere where these crosses are, and suppose you know what the degree of this polynomial is. Then by what I just told you, so you know that a polynomial of degree d has at most d zeros, then you know that there can be at most d crosses, right? So if you can find a polynomial of degree 10,000, which is 0 on all of your crosses, then you know that there can be at most 10,000 crosses. Okay, sounds easy. But of course, there's a big if in that second paragraph. You actually have to find that polynomial, and that's not so straightforward. Of course, I've also cheated because I've first told you about polynomials that had zeros on the real line, and then I said, oh, when you can define a polynomial that kind of has zeros in this cube. So it's a little more complicated than that, but by the standards of modern mathematics, it's still very elementary. Okay. The conclusion, or the upshot, is that basically it doesn't matter how you distribute the crosses in your cube. What matters is that you've actually placed sufficiently many. So they proved that if you place more than 2.756 to the n crosses in this 3x3x3 cube, you always get a modular line. What does that mean for noughts and crosses? If you were to play noughts and crosses on a side length 3 board in n dimensions, then because each player places half noughts, half of the total number of symbols, so player 1 will place half of 3 to the n crosses, and because for large value of n, that number is much bigger than 2.756 to the n, it means that that player has actually got 3 on a line. Okay? So when the dimension is large enough, noughts and crosses cannot end in a draw. And by a simple argument, it actually means that the first player has a winning strategy. Now, if you're still awake, you will have noticed that I really cheated here because, well, the first result was about modular lines, and noughts and crosses isn't. But it turns out that there is a very similar result for combinatorial, and hence for ordinary lines, that I actually was originally going to talk to you about before all these exciting things happened 6 weeks ago. It's called the density Hales-Jewett theorem. But so basically, even though what I've written is kind of false, it's still sort of true. Good. Now, we've spent the past 50 minutes pondering all kinds of fun questions about games and points and lines and cubes. But why should anyone care? We care because asking and answering difficult questions is a fundamentally human endeavor. All progress is ultimately driven by human curiosity, be it in mathematics, history, philosophy, physics, you name it. Sometimes, actually even a lot of the times, it's more about developing methods to solve these problems than it is about the problems themselves. So, for example, much of the work on this 3 on a line problem has contributed to developments in what we call discrete Fourier analysis, which is to do with signal processing, for example. The first proof of the Hales-Jewett theorem was actually used methods from a field of mathematics, a branch of mathematics that's called dynamical systems. So usually that studies how the movement of a pendulum, for example. So there are many, many unexpected connections. And eventually, some of these methods and connections will produce more serious and more practical applications. However, unlike what our government likes to think, these are often not predictable. And my favorite example for how unpredictable these applications can be is that of public key cryptography. So this is something, even if you haven't heard of public key cryptography, I'm almost certain that you have used it. So every time you purchase something on the internet, you send your credit card information safely and securely. There is a mathematical algorithm behind that, and that is based on a piece of very pure and abstract mathematics. It was discovered in the 17th century by Pierre Fermat, and I'm pretty sure Fermat didn't know that we were going to have the internet. So part of me doesn't even want to try and justify why this kind of mathematics is useful, but it so happens that in this particular case, I can actually point to two almost immediate applications, so I'm going to do it anyway. So one application is to what we call fast matrix multiplication. Now, a matrix is simply a very big array of numbers. Usually they don't move. And in many applications, in scientific computing and engineering, you want to multiply these arrays of numbers together very, very fast. And it turns out that this work on 3 crosses on a line actually has implications for how fast these algorithms can work. There's a second very quick thing I want to say. It can also help us establish properties of networks, large networks. So this can be networks of computers, of people. They can be extremely complex. And very often what we want to understand is what kind of properties these networks have globally. For example, how connected are they? Are there big clusters anywhere? But very often in practice, we can't really go and look at every single node in these networks because it's simply too big. So what we want to be able to do is just sample a small number of nodes from this network and be able to tell reliably what global properties this network might have. And again, these kinds of methods can help with that. Okay. But at the very least, if you're taking nothing else away from my talk, I hope that it has taught you to not fall for this one.
Okay, so we're gonna play.
Yeah.
All right. So we're gonna play tic-tac-toe. All right.
Yeah.
This is with a twist, right?
Okay.
If you win, then you get to smack me across the face. All right. If you don't win, then we kiss.
Do it. Okay.
So you saw what he did there? If you don't win, then we kiss. You've been warned. Thank you very much for your attention.
Often during your talk, you would say, what's the answer to this? We've no clue. How many of the problems that you've talked about are actually unknowable? The answer have answers that are unknowable rather than just unknown?
I think all of the answers are knowable, but we may not find the answer in the next 10, 20, or even 50 years. For example, so this minimum dimension that guarantees that you're going to have 3 on a line. So that has been proven to be a finite number. So as far as I'm concerned, it's perfectly knowable. We just don't know how to compute it. And I think that applies to all of the problems that I mentioned. They are all finite numbers, expressions that we ought to be able to derive, but we cannot.
Dr. Wolf, thank you very much for a most interesting and indeed nicely presented lecture. Going back to your first slide where you had simple noughts and crosses, it just occurred to me, assuming that the players know nothing really about the properties of this game, i.e. it would tend to end in a draw, I wonder why, but they can think strategically, why anybody would, the first player, the first mover in this game, would place his symbol, cross if you like, in anywhere other than the center, because if you take your first, the first player plays his first move in the center, there are 3 or 4 potential strategies moving vertically, horizontally, and across both diagonals. Now, if it's off the center, if you place the first player places his cross in any of the squares off the center, there's only 3 possible strategies. So I'm wondering why anybody would actually do that other than to cause mental confusion perhaps in the opponent.
So I'm actually not an expert at noughts and crosses. But I think, again, so if you did place your cross in the center, it wouldn't guarantee you a win. The best thing you would come out with is a draw. But your question has...
Why would they not actually put it on the center? Why would they not? Why would the
So, but your question has highlighted a very... So I asked one question during the talk, which is what is the winning strategy for the 3x3x3 game? And that is indeed to go in the center for precisely the reason that you mentioned, namely that you have the largest degree of freedom. In the two-dimensional game, it doesn't make any difference. You don't gain sufficiently. So you could, but you don't gain enough from it. But in 3 dimensions, yes, you do.
Hello. Just a sort of question about definitions. In the length 3,
Yeah.
you said that a modular line could be, say, 2, 3, 1.
Yes.
If you've got a length 4, does 3, 4, 2, 1 constitute a modular line, or would only 3, 4, 1, 2 constitute a modular line? I.e., does ordering matter?
It does, because I basically have to be able to draw it on my piece of paper and wrap it round, and then, yeah.
So in the game set, not
Yeah.
all... I know, because it's length 3.
It
But
only has
if you
length
played set in length 4, then you're not only looking for modular lines.
I think that is correct.
Okay,
Yes.
thank you.
I was wondering, you mentioned that you could play the Noughts and Crosses game or a more complicated version with more than 2 players. Now, sort of traditional Noughts and Crosses is played with 2 players, but how does increasing the number of players as well as the number of dimensions and the size of the grid affect the game in terms of, like, sort of whether it's drawn, whether it's easier to win, etc.?
So as far as the abstract mathematical result is concerned that I stated, the Hales-Jewett theorem, having more players makes it harder. Why does it make it harder? Because if there's 10 players, you know that you can only occupy 1/10 of the cube. I mean, you get to occupy fewer of the subcubes, right? So that means it's more likely to end in a draw. But the result says that if you play in sufficiently high dimension, at some point you can still guarantee that, that the first player wins. Does that answer your question? Thank you.
All the examples you pose are examples of a computable questions, so they can be solved. But I'm interested in the class of problems where, as the numbers become very great, and you've cited the wow function, you eventually end up where you have to, by brute force, go through so many possibilities. Just to store the data would need more atoms than there are in the universe. So we get a class of problems which aren't computable in the real world. And I'm just wondering what you think about that, whether you think there may be some breakthroughs ahead which might change that, or are there just some things that are unknowable, even though mathematically they are computable?
That is a very good question, but I'm really not qualified to answer it. I mean, I have... I'd really be speculating here. So I think all of these things are knowable. Yes, are they computable? Will they ever be computable by computers? I really don't know. But I would hope, I mean, my personal view is that we can understand mathematics well enough from a more abstract point of view that we won't actually need to compute anything. Yes.
You were talking about doing noughts and crosses in higher dimensions, but I was wondering whether there are winning strategies for using grids within grids. For example, you draw a 3x3 grid, and then in each box you draw another 3x3 grid, and you play in those grids.
I think I haven't understood your question, sorry.
Just wondering if there was a winning strategy for those sort of games.
Where you have a 3x3 grid.
And then you put smaller 3x3 grids inside those boxes. So you end up with 9 3x3 grids in a 3x3 grid.
Possibly. I'm not familiar with this game. Have you seen it played?
Yeah.
Yes? Okay. No, I'd have to go and look that up. Sorry.